In this video we're going to look at the Laplace transform of a derivative. So we're going to ask the question, if we have a function f of t, when we Laplace transform it, it gives us a function f of s. So what happens when we Laplace transform the f derivative of t? What's it going to give us? So we'll just go ahead and do that. So we're looking for the Laplace transform of f derivative of t, which is integral from 0 to infinity of f derivative of t times e to minus st by dt. Now we're going to rearrange this because we don't want f derivative of t in this. We want to get rid of the f derivative of t. We just want it to be f of t. Now one way of doing that is by using integration by parts. Now integration by parts, we met it in that previous video. So it's kind of like the chain rule for, it's kind of like the product rule for differentiation, but this is in effect a product rule for integration. So this allows us to swap in effect these derivatives. So the f derivative just becomes f, and then we end up with a derivative of this term. So let's go ahead and we'll do that. So the product rule for integration tells us that if we have the integral from a function u dv equals u times v minus integral v du. So we'll choose our values for our u and dv. So we'll let f derivative t equal the dv and let e to the minus st equal u. So that means that whenever we integrate this here, we'll get left with our f of t, and the other side will just be left with the value of v. And the same goes here, the e to the minus st, and that becomes u. Whenever we differentiate this side here, du, then we differentiate that side there, so du is going to equal minus s e to the minus st. So it's just a matter of now plugging these values into the equation above. So in the equation above we've got u times v. So u is just going to be e to minus st, and v is just going to be our function f of t. So we get e to minus st f of t, and that's from 0 to infinity. And it's going to be minus the integral of, well, it's just going to be our v times du. So our v is our f of t, and our du is minus s e to minus st by dt. So this remains the same here. We can take out the factor of s, so the minus cancels out, just end up with the s. Integral from 0 to infinity of f of t e to minus st by dt. Now we can see that we've designed the Laplace transform so that the limit as t tends to infinity of our function e to minus st f of t must equal 0, so it must converge as t tends towards infinity. So it means that from this part of the equation here, when we put our infinity in here for our function t, we're going to get a value of 0. And whenever we put the 0 in, well, e to the minus 0 is just 1, and then you'll be left with the f of 0. Also, this thing here is nothing else other than the s times this thing here, which is just going to be the Laplace transform f of s. So eventually you can write the, if you have a function f derivative of t, the Laplace transform of that function is just going to be s times the f of s minus the f of 0, which is this section here. So let's go ahead and we'll look and see what happens when you look at the second derivative and the third derivative. So if we wanted to find the Laplace transform of the second derivative, we just use an iterative method. So we're going to look at it, it's going to be the s times the Laplace transform of the derivative minus f derivative of 0. So we'll just use what we've seen in the previous page, and we're just iterating it out to the second derivative. So that's going to be s times, well, the Laplace transform of f derivative of t is going to be s times f of s minus f of 0 minus f derivative of 0. So finally we can say that the Laplace transform of the second derivative is going to be s squared f of s minus s f of 0 minus f derivative of 0. And you can work it through to get the third one. So the third derivative will be s cubed f of s minus s squared f of 0 minus s f derivative of 0 minus f double derivative of 0. And then if we wanted to, we can extend that out to the nth derivative, or the kth derivative, the nth derivative, and it's going to be s to the n of f of s minus this factor here, p of s, and the p of s is going to be the sum from k equals 1 to n of s of n minus k f of k minus 1 f of 0. Now it's a bit of a mouthful this here, and most of the time we're going to go through some examples. It'll be the first, second and the third order derivatives that we're looking at, and we're going to look at an example on the next page, and it makes it a bit plainer and a bit clearer as to what we're doing, and it shows you the power of using Laplace transforms in order to solve differential equations. So let's solve a differential equation using Laplace transforms. So if we had this differential equation here, so the second derivative of time plus 4 times the first derivative of time plus 5 times the function of time is equal to 5 times the step function u of t. So what we have to do is we've got to replace the derivatives here. So we know that the second derivative is going to be replaced by s squared f of s minus sf of 0 minus f derivative of 0. And then the first derivative can be replaced by sf of s minus f of 0, and that's going to be times 4. And the f of t here will now be the f of s, it will be 5 times the f of s. And when we take the Laplace transform of 5 times u of t, it's going to be equal 5 times 1 upon s, which is just 5 upon s. We then look at the initial conditions. So initial conditions, f of 0 equals 1 and f derivative of 0 equals 2. So we stick the initial conditions in here for the values here of f of 0 and f derivative of 0. So that's going to leave us a s squared f of s minus s minus 2 plus 4s f of s minus 4 plus 5 f of s equals 5 upon s. And now all we need to do is take out the factor of f of s, and in the brackets you'll have s squared plus 4s plus 5, and we can take the rest of this here over to the other side. We'll have 5 upon s plus 6. So then what we want to do is we want to just have a single equation, f of s equals, so this final end up f of s equals s squared plus 6s plus 5 upon s squared plus 4s plus 5. So I suggest you work through that yourself and convince yourself that the algebra is correct. So now we can see that in order to solve this differential equation, what we can do is put everything into the s domain, and rather than having difficult differentiations to do, or possibly integrations if it's an integral differential equation, all we're going to do is just simple algebra, and we're left with this final function at the end. And what we can do is we can use a table of Laplace transforms in order to transform that back to the time domain, and we'll have a full solution of this differential equation. So this is really the real power behind using Laplace transforms. So thank you for listening. I'll get you on the next video. Goodbye.